Greetings and welcome. In today's video, we're starting a new concept, a whole new chapter really, on combinatorics and probability. And the section we're specifically looking at is called Permutations and Combinations. All right. And just as a brief introduction, combinatorics is the study of the number of ways an event can occur. All right. So it's kind of counting the number of combinations, I guess, is a loose way I could refer to it, but permutations are another type we'll talk about in this video as well. So let's start off with an example for us to consider. Suppose each day when I get dressed, I've got 2 pairs of pants, 3 shirts, and 2 ties. All right. And I just randomly reach into my closet and grab one of each item every day, and I'm not concerned about whether or not the items match. And I want to figure out how many ways could this happen? How many different combinations of outfits, so to speak, could I have? One of the ways we can do this is with a tree diagram, in which I'll draw kind of the sample set of all possibilities. So my first decision is pants, and I can grab pants pair 1 or pants pair 2. All right. My second decision would be shirts. So once I've gotten my pair of pants chosen, I have 3 shirts I could choose from. Right. I could have shirt 1, shirt 2, shirt 3, or if I chose pants 2, shirt 1, shirt 2, shirt 3. Right. So the number of branching possibilities is increasing, right? So, for instance, this endpoint here would be in the world in which I chose pants 1 and shirt 3, or this is pants 2 and shirt 1, right? So you can kind of see that each of these endpoints represents one of the unique possibilities. And then lastly, I've got my 2 ties. So off of each of these, I have tie 1, tie 2. Right, so I've got 2 decisions off of each of those, right? So with all of these branching possibilities, now I can figure out how many ways this could happen. And the way I could count this is by counting all of the endpoints. All right, so this endpoint here, I just want to point out, would be the day in which I happen to choose pants pair 1 with shirt number 2 and tie number 2. Right, is the situation that would be occurring there. Oh dear. It looks like I just dropped, just a moment. My writing tablet timed out on me or something. Here we go. So to count the number of ways that this happens, all I have to do is count these endpoints. So there's 1, 2, 3, 4, 5, 6. And there are 12 ways that this could occur. Right? And once again, that's the universe in which I don't care whether or not I am matching at all. Right? Which, hey, that does happen sometimes. In which I'll wear my brown belt with my black shoes or whatever. So this is kind of our introduction to ways of counting the number of ways something can occur. Right? That's the study of combinatorics. And there is a simpler way to doing this, where I could have taken the number of ways each individual event could occur and multiplied them. All right, so I could have done 2 times 3 times 2 and gotten 12 ways that way. And the reason I could have done this is because these events were independent events of one another, at least in the problem I described, where whether I chose pants pair 1 or 2, it didn't have an effect on which shirt I chose, right? There were still 3 outcomes for each of those. Or it didn't affect which tie I chose with that combination, right? So because all of these events were independent, I could multiply the number of ways each individual decision occurred to get the total number of ways that could happen. So that's the idea of independent events. All right, so independent events are events that have no effect on one another. So examples of independent events would be like flipping two coins, right? So kind of example, flipping two coins, where getting a heads on the first coin would not change the outcome on the second coin, right? Or drawing a card from a deck, putting the card back, reshuffling, and drawing another card. Because I put the card back, the number of ways that it could happen the first time is independent of the number of ways the second time, right? It wouldn't matter. Or rolling two dice, or flipping a coin and rolling a die, right? Whatever decisions I'm making, the events are independent if they have no effect on one another. So, and contrary to that would be dependent events. Where my two events do have an effect on one another, and examples of that would be like drawing two cards from the same deck, right? Where, for instance, if I wanted to figure out how many ways could I draw an ace from a deck of 52 cards, the first time I draw it, there are 4 aces to choose from. And the second time I draw it, because I just previously drew an ace, there are fewer to choose from, right? So the second drawing was affected by the first. So those would be examples of dependent events. All right. So it's kind of an interesting little, I guess, story, somewhat of an abstract concept. My older brother, when he took a statistics and probability class in college, his professor started it with this idea. And I think it's kind of interesting. Let's see if I can draw this. This is my picture of an airplane here. Right, so here's an airplane. And the professor said, starting the class, that suppose, all right, now this is somewhat, I guess, politically incorrect, but suppose the probability of a bomb being on a plane, all right, so here's my little bomb, is a particular probability. Let's say it happens to be 1 in a million. All right. Now it's clearly not the case, but let's say hypothetically that was the case. So what the professor said he would do, right, if he has a fear of flying, right, worried about things like that, he would say that when he would go flying, he would bring his own bomb on the plane, because what's the probability of 2 bombs being on the same plane, right? And you could argue, okay, those would be 2 independent events, so that would be like 1 out of a million, right? Multiplied by 1 out of a million, and that's going to be very unlikely. So this professor's really safe, right? Because he's not planning on detonating his bomb, he's just planning on bringing it on to reduce the chance of another bomb being there, right? So let's see. So the chances that would happen would be 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Right? Very rare, right? I think that's a trillion, right? In our hypothetical situation. So I guess my question to you is the professor actually any safer if he brings his own bomb on the plane? Because, right, what's the chance of 2 bombs being on the same plane? And I guess we could break this down. First of all, are these 2 events independent or dependent? And you would argue that yes, they are independent, right? Whether or not he brings his bomb wouldn't have an effect on whether or not, right, some terrorist group was planning on attacking the plane that day, right? However, this is kind of a trick question, because since the professor is aware of the probability, he isn't a 1 out of a million chance of his bomb being on the plane. His situation is actually a guaranteed situation, unless, of course, he gets stopped in customs or TSA or whatever. The number of ways his event could happen is 1 out of 1. It's guaranteed, right? Where he's for certain planning on bringing his bomb on the plane. and it would therefore not improve his odds of there not being someone else with the bomb that day. So even though these two events are independent of one another, the trick is in the fact that he's kind of trying to control the statistics to his favor, right? Which doesn't really work. Whereas this situation would kind of be like the awkward situation where if you were on a plane and simultaneously one terrorist stands up and says, "I've got a bomb," and like then in another row someone else also at the same time stood up and said, "I've got a bomb," and then they awkwardly look at each other and like, "Oh no, like we're both trying to hijack the same plane at the same time. I guess we should have coordinated this," right? Like they were independently doing it at the same time, which would be an actually really rare event, right? Something like that. So not to instill fear in anyone, I don't think this is actually the probability of this occurring, but nonetheless, it brings up the concept of independent events, dependent events, right, and things like that. So regarding independent events, we've got this idea of the basic counting principle is the way we can handle it. And let's see. I think what I'm going to do is just grab a snapshot for sake of time right from the text. Oh, looks like my text has got the blurries. And the basic counting principle says this. Let's see. Come on. Are we focusing here? Focus. All right, it says, suppose one event can be chosen in P different ways, and another event, another independent event, can be chosen in Q different ways. Then the number of ways the two events can be chosen successively is P times Q ways. All right, so this is called the basic counting principle, a way of instead of drawing that tree diagram like we did earlier, because the events were independent of one another, I can just multiply the individual outcomes or numbers of ways those could occur to get the total number of ways they could occur, merely because these were independent. All right, so the basic counting principle would not apply in other situations. All right, so that is called the basic counting principle. All right, so let's do an example of that. Let's suppose we have a 6-digit license plate number. All right, 6-digit license plate. All right, and let's consider a couple cases. So let's say our first case is that the first 3 digits are letters, and the last 3 are numbers. All right. So our situation looks something like this, where I've got 1, 2, 3, 4, 5, 6 individual spaces represented. The first 3 are letters, the last 3 are numbers. So any individual letter or number has no effect on the other ones. It doesn't have a rule saying that if you have an F in your plate, you can't have another F show up or something like that. So these are, in fact, independent decisions of one another if we have randomly chosen license plate. So the first letter being chosen, how many ways or how many different letters can I choose from? Well, that would be 26. The second letter being chosen would be 26. The third being chosen would be 26, right? Since there's no outcome on one another, right? And then as far as the 3 numbers, how many numbers can I choose from for the first digit? Some people would wrongly say, all right, the numbers 1 through 9. So there's 9, which is wrong because I also could have a 0 as a digit. So there is actually 10 possible numbers there, times 10 times 10 times 10. And I could multiply that all out, and that would give me the number of ways that that could happen. All right. So because these are independent events, I can multiply these individual probabilities using the basic counting principle. So let's do another problem here. Suppose, let's see. Suppose that any digit could be a letter or number. right? So that's going to increase the number of possibilities in both situations. Let's see, 1, 2, 3, 4, 5, 6. So for our first case, there are 26 letters I could choose from and 10 numbers, a total of 36 outcomes, right? And each of these would be 36 times 36, right? So lots of possibilities, which actually I guess this is 36 to the 6th power. It's a lot, right? Kind of like how this, I guess, was 26 to the 3rd times 10 to the 3rd. A lot, right? And in this case, this is actually a much bigger number than this one. We could try to calculate that out if we wanted. So having more possibilities for each decision will actually increase the number of ways that could occur, right? And these were independent events of one another. Now here's a dependent event situation. Suppose it's the same as type B, so they could be any letter or number, but no repetition. Right? So in this case, these are dependent on one another, because once I've chosen one outcome for the first, right, there's 36 symbols I could choose for the first, but I've chosen one already, so there's one fewer decisions or possible outcomes for the second, and then one fewer after that, and one fewer after that, and so forth. So I actually have fewer outcomes for each, but I can actually still multiply these, is the way it works out. But it's not 36 for all of them. And then clearly if I wanted a greater number of possible license plates, I could actually, then include an alphanumeric, character or some non-alphanumeric, such as equal signs or slashes or whatever else I wanted to increase the number of in each decision, and then kind of have more possible outcomes there as well. So let's see. Let's do one more quick example. So suppose in choosing a password, what's the probability that, let's say we've got, 5 digits. And what's the number of ways it could end in a number? Ends in a number. Where the first digits could be letters or numbers. Let's say 1, 2, 3, 4, 5. So there are 36 combinations, 36, 36, 36, and then ending in a number there are only 10 combinations, right? So I could multiply those all out to get that possible value, right? And then here's kind of a more difficult question. What if there's exactly one number but I don't know where it is? And now this is kind of a trickier situation because I could have the number show up in the first location where there's 10 possible outcomes and exactly one number, so meaning the other digits must have been letters, so 26, 26, 26, 26. But this isn't the only possible way this could have occurred. I also could have had 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. I also could have had the number show up in the second digit, or third digit, or fourth digit, or fifth digit, for a total of 5. I was excited about my curly bracket there, and then it failed on me. So there are 5 separate ways that this could occur based on where the number could land, right? So the answer to this question would be 5 times 10 times 26 to the 4th, where I have to actually take into account where that number lands. So there's all sorts of different ways that these problems can get slightly more complicated in things like that. But it's kind of the idea you have to figure out, is it independent, is it dependent, and what is going on in the situation. Let's see. I think I've got one more thing for us to consider. Which is permutations. Which is an arrangement of objects in which order matters. Right. So, kind of like this previous example, this is somewhat of a permutation because the location of the 10 mattered to us. We considered these 5 separate situations as opposed to, just it doesn't matter where the number lands, or saying like the number was ending in a number, right, or something like that. That the location changed the possible number of outcomes. So examples of this would be like someone's phone number, right? When I ask for someone's phone number, they don't just give me 7 digits that happen to make up their phone number, and I'm like, okay, and then I just go and dial that number in any order that I'd like. That's not going to likely give me the person that I'm looking for. The order of the digits matters, right? So phone number, another example would be kind of a parade, right? Where typically in a parade, it's not just a matter of how many ways can we have these people arranged, but the actual order in the parade matters. The reason I'm choosing letters that start with P is for permutations to kind of remind me of, okay, phone number, order matters. Parade, the order matters, right? We want kind of, the more important people to land in a particular spot on the parade as they come down the way, right? So, so order matters in situations like ranking. So consider what if I've got 5 horses in a race, and I want to figure out how many ways they could be ranked. All right. So, well, there are some possibilities. So let's say that for first place, there are 5 horses that could have gotten first place, right? 5 to choose from. For second place, there are 4. For third place, there are 3. For fourth place, there are 2. And then last place, there's only going to be 1 horse left to choose from because I've kind of chosen all of the rest. So I could actually figure this out by multiplying each of these subsequent numbers. Now in this situation, I actually happen to have created what's called a factorial, which looks like this. So this is actually 5 factorial, and what I mean by factorial, so if I have n factorial, it's denoted by an exclamation mark, so that's not n like all excited, that's just n factorial is how that's read. It means n times n minus 1 times n minus 2 times n minus 3. So I'm multiplying it by one number smaller than itself, multiplied by all the way down to 3 times 2 times 1. Now in this case, there weren't this many terms represented, but you get the idea of factorial of it's just multiplying a number by all of the numbers 1 digit less than it, all the way down to 1. And n is going to be restricted to being an integer, a positive integer as well. So the way that works out. Actually, I think I lied. There will be 0 factorials that we'll have to consider later. And 0 factorial is actually defined as being 1, which is really weird. But it happens to mathematically work out the best that way. So, so if I wanted to calculate what is 3 factorial, for instance, that just means 3 times 2 times 1, which is 6, right? Something like that. Or 4 factorial is 4 times 3 times 2 times 1. Or let's see, 6 times 4 is 24, right? So I can figure that out, doing stuff like that. And in terms of permutations, we're actually going to define them in terms of factorials. So a permutation of n objects taken n at a time, all right, which is kind of a weird way to describe it, but you'll see what I'm saying, will be defined as P of n comma n, so n objects taken n at a time, right? So arranging 5 horses in 5 rankings will be defined as n factorial, right? Which is what we'd found earlier. So that kind of works out nicely. Whereas the permutation of n objects taken r at a time let's see, barely fits, will be P of n comma r, which is defined as the formula n factorial divided by n minus r all factorial. And so that's kind of a little bit trickier there. But I will have kind of an explanation and a derivation of that in my next video. But let's consider the example. What if I've got 5 horses in the race and I only have 3 ranks, right? 3 places to give them. The way I could figure this out is the permutation of 5 comma 3, which is 5 factorial over 5 minus 3 all factorial. So that denominator 5 minus 3 is 2, so that's the same as 2 factorial, right? And 5 factorial just means 5 times 4 times 3 times 2, technically times 1, right? Or I could have also thought of that as just being 2 factorial, right? 2 factorial just means 2 times 1, so it's another way of representing it. These would cancel out, and I'd get 5 times 4 times 3. 5 times 4 is 20 times 3. There would be 60 ways for the horses to be ranked for tiers 1 to 3. Alright, so here's our basic introduction on permutations and combinations. Clearly I didn't get far into combinations since I didn't define it for you yet, but there will be other videos that you can reference for that. Thanks for watching, and I'll talk to you later.